Greetings. Last time we were talking about having a fuzzy inference system and then training the fuzzy inference system, tuning it, if you will, using actual training data. There are literally hundreds, and I literally mean hundreds of papers on different techniques to tune fuzzy systems with data. I actually had a student one time do a survey paper on them, and the literature hits that he got were just incredible. So what we're showing you is one specific way to do it. There are a plethora of other ways to tune the fuzzy system to give you superior results. There are additional things one can do in training fuzzy systems. We have looked at being able to train the parameters of the membership functions for the antecedent. We can also train it for the consequent. We can also train for the number of membership functions. You remember in a neural network, if we had too many neurons, and a membership function is kind of like a neuron. If we had too many neurons, it's a degree of freedom. What happens? We overlearn. We learn too much. We begin to memorize. Such can be the case in a fuzzy system also. If we have too many fuzzy membership functions, well, that isn't good, because we're going to be memorizing instead of learning the situation. There are two approaches to determining the optimal number of membership functions. One was pioneered by Jerry Mendel, and it was called the concept is as follows. It was referred to as dynamic membership function creation. One starts with just a few membership functions and then begins to add on membership functions until one reaches a point of equilibrium between the generalization and the generalization and the actual training error. So that's one way to go, is to start with one and go to many. Another way to do it is to start from many and go to a few. And that's the one that we're going to look at a little bit more in detail. How do we start with many and go to a few? Well, if we go from many and go to a few, we have to have some reasons for ridding ourselves of membership functions. There is a chapter in the book, which we did not cover, which is called Pruning Methods, which was a technique for actually extracting neurons from a neural network in order to affect better generalization. And a lot of it had to do with the use of a neuron and whether the neuron was actually contributing to the neural network in a fashion that was acceptable. Come on over and have a seat. Yes, sir. Don't be shy. It's good to see you. And we're going to do something similar. We're going to look at these membership functions as we evolve in the training, and we're going to look at a point where membership functions become useless to each other, and therefore we can discard them. There are two ways that we will do things. We will either combine membership functions or perform a fusion, or we will simply throw away a membership function or annihilate it. So the process that we're going through is fusion and annihilation. And the question is, when do you fuse and when do you annihilate? Here are the basic ideas, and then we'll give you the specific reasons for it. The first one for fusion, excuse me one second. For the concept of fusion, we have the following situation. Suppose, for example, that we have Gaussian membership functions as opposed to the triangular membership functions, because that's what we're using in this example. And we were, in the process of iteration, we found that two membership functions were assigned the same sort of consequent, but they were very, very close to each other. Right? They were very, very close to each other, almost overlapping each other. In such a case, one of them isn't necessary. Does that make sense? So in the process of tuning, when two of them become too close together, we perform a fusion operation. And in the fusion operation, we actually replace the two membership functions here by a single membership function. You'll notice that does a couple of things. That lowers the number of membership functions, and also in the rule table, Here's the antecedents if we do it for the antecedents, and we had this membership function and this membership function, and they both had the same antecedents, such as, I don't know what F stands for, high, very low, okay, and high, and very high, low, low, high. And if these were doing the equivalent thing, we could literally perform a fusion of these two in order to get the proper result. Now, of course, when we perform the fusion, the new fusion now would take the single row or the double row and replace it by a single row. The question is, what if these two membership functions get close to each other and these differ? In order to have them differ, we might have them matching everywhere, but have low and very low here. And the question is, could we fuse them if indeed we have that sort of scenario? The answer is yes, we could fuse them, but once we fuse them, we have to decide what to put in the new table entry when we perform the fusion operation. And so we can do that many times by actually looking at the training data and seeing where the training data for this antecedent actually brings this result for the complementary antecedent, and be able to replace those. Now, I think you can see that the underlying heuristics are very solid. It makes a lot of sense heuristically. If these things get close, they're doing the same thing, then you have a duplication of effort, and you can actually get rid of one of the membership functions. Once you have these heuristics, there's a number of ways you can impose those heuristics by defining what you mean when two membership functions are close to each other, etc. There's some math in the papers, and you can look at that, but the basic concept is for fusion is that, number one, the membership functions have to be close together, number one, and number two is that the rule table corresponding to these two membership functions must be close to each other in some sense, so that when we perform the fusion. The second one is annihilation, and I don't know how to spell annihilation, so I have to look it up. There we go. Annihilation occurs when the following happens. Suppose that in the process of training the mean and the variance of the membership functions, which is essentially what we did for the triangles, we were able to get a number of membership functions, but one of the membership functions starts to do something very interestingly. It starts to become very, very narrow. Well, if there is not an underlying purpose for this narrowness, it is a chance that this is really just some chaff in the wheat that we need to rid ourselves of. It's a distraction to what is going on. It will not be a distraction if indeed there's a very important contribution in this area. The underlying criteria is that the overall decision function generated by the fuzzy system is smooth, which indeed it characteristically is. That's the reason we use fuzzy logic and fuzzy inference engines, is because they give a very smooth sort of transitions. So in the case where you want a very smooth transition in your control, it's many times that this becomes sufficiently small that we can simply annihilate it. We can simply rid ourselves of it. The math is telling us that that membership function isn't required. It's extra baggage. We can get rid of it. So this is the process of the annihilation. Now, in the annihilation, of course, we will replace the result once it gets sufficiently small. We will replace it with the original membership functions and keep it in this fashion. And the rule table for annihilation is very simple. If you have a rule table and you have a rule here which are annihilated, well, it simply means that you get rid of that whole row of the rule table. You don't have to worry about that anymore because you've annihilated it. So that's the process. So how does this work? Well, typically the way it works is as follows. One would train using training data, and one would look at the generalization of the training error. And so one would actually look at the error as a function of the epochs. and the errors would typically go down, and we're not doing any fusion annihilation. We would wait until we get a flat spot here. When we get a flat spot, we'll look at what we converge to, and we will see that if in this flat spot there are any membership functions which can be fused or annihilated. Then we either fuse them or annihilate them, and guess what happens to the error when we fuse and annihilate them? It pops back up, right? Because in a way we have optimized for this being for the fixed number. So we perform fusion and annihilation, and then we begin the training process again with fewer membership functions, and it is very typical, as we generalize better, that the error curve actually goes to a lower point when we actually train some more. So we get actually better generalization. So we perform a fusion and annihilation again, we train again, and we do fusion and annihilation, and we'll eventually get to the case where, guess what happens? The error here becomes higher than the error here in terms of the training. What does this mean? That means we go back and we stop here and we keep whatever is here as the best fuzzy system for our particular example. So does that make sense? So again, we perform the training where we adjust the membership functions, and then we perform a fusion and annihilation, and we do a training again, and hopefully the error decreases each time in order to get us to a result. Now, in order to do this, I'm going to give you a kind of a pedagogical example where in a very simple case, there was an attempt to train a simple product of cosines. Very, very simple result. So if we could zoom in on here. Thank you, those three. Ooh, psychedelic. A little bit. So this is just kind of a cosine x, cosine y rotated by 45 degrees that you're looking at. And we see here is the original value. Now, if one was to look at a fuzzy membership function, just setting it up by heuristics, that if x was in this region and y was in this region, then the result would be high. It's kind of a cosine squared sort of thing. If one just looks at heuristics for setting up the fuzzy membership functions here, one obtains this result. This is just setting it up by heuristics. And then after training, one was able to train it to this result, which was a lot better. The rule table let's see. The rule table for the original membership function is somewhere. And it was set up heuristically. And let me show you what happened in the training. It's very interesting. Let me get my page numbers correct here. This is 706, 707. I'm missing 703, 704, and 70. Oh, there's 703. Hi, 703, 704, 705. Okay, here we have on the top the initial guesses at the membership function. This is for a fixed rule table now. So this is the value of x, this is the value of y, and this is the fuzzy membership function for the antecedent. So using this cosine squared table and by generating data from this admittedly pedagogical example, the process was repeated, and these were trained and tuned in accordance to the steepest descent optimization that we talked about previously last lecture. And the result that we got after convergence was this result here. Now, this was the input, and the corresponding output. Well, it turned out by the criteria that that was chosen for annihilation that this membership function in the middle here was sufficiently small where it could be annihilated in the next step. So from going from these three to these three, we do the fusion and annihilation. So in this case, this one was annihilated. These two in the beginning were actually close enough to be fused into a single membership function. And these are criteria you can set by math. You can define what you mean by closeness, if you will. And in a similar fashion, let's see what else we did. Oh, actually, these three were close enough to be fused into a single one. these two were kept, and these two were kept also. So as a result, this was a result of the first training followed by the fusion and the annihilation. So starting from here, the error went up as soon as the fusion and the annihilation started. After the fusion and the annihilation started, it was trained until convergence again. Well, for the second convergence, we have these three results for the two inputs and the output, and you can see something interesting that's happened is that the membership functions here have started to squeeze together, and clearly for this antecedent we have a membership function that we can annihilate here. So the process of the fusion and the annihilation, ignore the bottom two plots, was that this was annihilated going to here, and these two were annihilated going to here. Let's see, I don't see any fusion, but I'm sure it took place. Clearly this one was annihilated. So this again got the error shooting up, and then the training continued. And I think you can see the pattern which is emerging. After some more training, this was achieved. And here we had some more annihilation, some more fusion. More training. After some more training, there was, this was kept the same. There was some fusion here. The output membership functions looked about the same, a little bit more, and it finally converged to something very, very similar. And in this case, there was no criteria for any additional fusion and annihilation. So the stop criteria on this was that our fusion and annihilation thresholds, which we set for closeness and narrowness, were no longer exceeded, and so this was the final result. And this had significantly lower error than was started with. So you can see the entire point here is not to go through the details of this, but to show that you can not only parameterize and you can tune the membership functions, but you can also tune the cardinality, the number of membership functions which are used in the actual generalization. And this will allow us to get to obtain better results. Okay, any questions on that? Are there other things you could tune in fuzzy membership functions? Yes, you could. You can, any place that you can put a knob, you can tune that knob in some fashion. You could, for example, if you wanted to, use a fuzzy membership function instead of a Gaussian, kind of e to the minus x minus mean over sigma, and then put this to the bth power. In other words, this is a sigma sort of membership function, and then you have a b up here, which makes it, if b is 2, it's a Gaussian. If b is 1, it's a Laplace, right? Double-sided exponential. So you could tune b if you wanted to. Okay? And you're just limited by your cleverness of putting these things in. In general, however, the tuning is traditionally, if you look at the literature, mostly been applied to the inputs and the consequences. The consequence, membership functions. You could also tune the logic. You remember Jaeger's Jaeger's union and intersection operators were parameterized by alpha or a lambda or something. You could tune that too, keep everything else the same. So there's no shortage of things which can be tuned in order to obtain these really neat results. Any questions at all? Okay. Let me mention to you that we will have a final exam in here. I've decided the final exam, like the midterm, will be take-home. I'm going to give it to you on Thursday at the end of class, and you'll have 1 week until the following Thursday to 5 o'clock to do it. Does that sound good? It'll be commensurate with your normal exam. If you want to go home early and all your other exams end early, you're welcome to hand it in early if you'd like to. You don't have to wait until Thursday to hand it in. The rules are the same. You're welcome to use any non-human information that you that you have available, except for me. And that's that awkward statement again, isn't it? You're allowed to use me. Okay, you're allowed to use me and not other non-human. You know what I mean. I'm the only human you can use for sources, is what I mean. Okay. Next thing I wanted to talk about a little bit was inversion of neural networks. There's all sorts of fascinating things one can do once one has a neural network trained. It's really remarkable. One can, for example, evaluate sensitivities very easily, and one can do inversion. What do I mean by inversion? Well, we don't even have to talk about neural networks in order to talk about inversion. Let me get the paper I wanted to look at in order to use the same notation that's used there. Yeah, here's the basic concept. We have, for inversion, by the way, this is just general inversion. We have an output y which is equal to a function of an input vector. This is an arbitrary function. Now this could be a neural network, for example. This input vector can be a bunch of stuff. We can have a neural network and have the output y be the corresponding output. And all of these weights and sigmoid nonlinearities and everything else can be collapsed into a single function we call f. Now the function that we've drawn here is referred to as having no memory. It's a memoryless nonlinearity in the sense that the output is only a function of the current input. It doesn't have any information about what the previous input was or the input before that was. It's just instantaneous. Whatever the input is now, you're going to have a corresponding output. Now what we would like to do is we would like to form an inversion of this. Now in general, we can look at f of x, at least in 2 dimensions, and we can perform a contour plot, if you will. We can look at values of f of x for which f of x is equal to a constant. In fact, we do have f of x is equal to a constant here. Say that this is f of x is equal to 1/2 or 1/3, for example. So all of these points on this contour, correspond to values of the input which will give you a corresponding output of 1/3. Now inversion of the neural network asks the following question. If you have an output of 1/3, what values of the input give you that output of 1/3? So in other words, the roles of input and output are reversed in the inversion problem. Now the challenge is that in many cases the inverse is not unique. As you can see here, for fx is equal to 1/3, we do not have a mapping to a unique output, but rather we have a mapping to a whole range of outputs. And so this is a challenge of inversion of the inverse problem in general, and we're going to have a number of corresponding outputs. Now, what are some uses in this sort of thing? Well, there's a number of very fascinating uses. Let me tell you one is the first one that I heard of in terms of neural networks being used for inversion. That was some work which was done at Johns Hopkins Applied Physics Lab by Russ Eberhardt, who actually took a neural network way back in the early days, the late 80s, if you will, of neural networks, and he trained a neural network on a disease. I even forget what the disease is. I should go back and look at the paper. But it was like one had a temperature and one had hives, the degree of hives or something like that. And then the output was the degree to which you had, I don't know, typhoid or something. Okay? So it was a diagnosis sort of machine. Neural networks, by the way, are very good at diagnosis in the medical field. The results have just been incredible. However, their adoption in the medical field has been less acceptable. Interestingly, not because of the fact that they don't work well. It's just the political acceptance of them. The physicians, of course, pride themselves on the art of their diagnosis, and they don't want to be replaced by neural networks. However, I think the obvious nice future of neural networks and that sort of thing would be as an assistant to the physician and making the final diagnosis. Don't have the neural network replace the physician, but just have that. Okay, well anyway, this is the idea. And can you see this happening? You get a bunch of people with typhoid and a bunch of people that are healthy, and you generate training data for a classifier to tell if the person has typhoid or doesn't have typhoid. Well, now the interesting thing happens. You train this neural network, and then you ask your question, the inverse problem. If a person has typhoid, what are the ranges of values that one could have for symptoms in order to give typhoid? You see, that's an inverse problem. And indeed, Eberhardt and his group addressed that and were able to come out with some very relevant, consistent data for the disease that they chose, which wasn't typhoid, that showed that the range of these different symptoms exactly were things which gave rise to typhoid. A place where neural networks are particularly interesting is in the case where one has an oracle, and this is for inversion. Now, an oracle is a source of truth, and usually this truth will cost you money. Data costs you money. Training data costs you money. So what happens is you give the oracle $1, and it will give you some truth. Now, what would be examples of this? Well, an example of this would be a case where in order to obtain your data, you had to go on a field trip, right? So it cost you time and money. Another very common type of oracle is a very computationally intensive piece of software with input-output relationships, finite element models, input-output relationships, wherein to get a single data point, it takes you a half hour, an hour to 2 hours in order to generate a single number. Now, that's an oracle. You can get truth out of it, but it costs you, not specifically money here, it would cost you in terms of the time for running the computer program. So here's the situation. You would like to train a neural network. You would like to train a neural network in such a manner that this neural network emulated this oracle, that it captured it. I think in the beginning of the course we talked about Invasion of the Body Snatchers. Anybody watched that since then? It's where you put a pod by a human being, and that pod began to take on the form of the human being and eventually replaced it. Well, that's what the neural network does. You put it next to here, and in the oracle, it began to take on the shape and eventually was able to do the same thing the oracle would do, except now you don't have to, neural networks are cheap, especially if you have a computationally intensive software over here. If you train this neural network, you can get your results like that. One of the things that was done by our group, which actually Megan was involved in, was the use of neural networks in time lag sort of mapping. And I'll show you this result. This is on the web, and there's a little link to it. Ah, here we go. Now, this software is for, I hope it's running. Yes, okay. This is software for actually looking under the sea and looking at the following situation. One has what's called bathymetry, which is the bottom of the sea, and then one has the top of the sea, and then one has some sonar, and this sonar pings out according to some parameters. Now, depending on a lot of the environment and a lot of what's happening in the ocean, such as how fast the sound travels, how rough the surface is, how rough the bottom is, the sonar is going to be able to insonify or cover this water column differently according to the parameters that you choose. Now, what's interesting is that there are some acoustic emulation programs which will allow you to do that. But the problem is that you choose one of these sets of parameters, and you sit there for a long time waiting for this emulator to compute the result for one insonification. In other words, it's a very computationally intensive sort of software. And if you move, if you change any of the parameters, well, then you have to start your computation again. Well, this is an example of computationally intensive software where in the oracle was used to actually generate data to train a neural network, and after a while, just like Invasion of the Body Snatchers, the pod was able to take on the same form as the neural network. I'm sorry, as the original emulator. Here, for example, is the insonification, and what you have here is the bathymetry, and this is actually the neural network, and it really works very nicely. One of the things that's nice, we can move over here a little bit. Can we get this in? No, bigger. Yeah, oh, okay, good. Here we have something which is called the sound speed profile. It's the velocity of sound at different depths in the water column. And one can actually, this is really interesting. What happens is if there is an indentation of the sound speed profile like we have here, it acts like an acoustic lens, which actually focuses the energy like a lens would focus light. And you can see that we make the lens, and look what happens when I wiggle this one little parameter back and forth, that, okay, now we don't have a lens, and bloom, now we do have a lens. So you can see that they come in. And the interesting thing, again, is that this result is nearly instantaneous. You do not have to wait for all of those different results to compute on the acoustic model in order to compute the output and the insonification, which is really nice. And there's other parameters that can be controlled also. So, okay, this is the bathymetry, which is the bottom of the ocean, and we've assumed a 3-dot model. So clearly when the sound goes down, you can see the sound goes down here and bounces off the bottom. Okay, and it's just a 3-point emulation. So the neural network was actually trained on this and can do the same calculations in the wink of an eye. The problem, of course, if you've watched Invasion of the Body Snatchers, you all have to watch that now, is that the replication was imperfect. One of the things is that I believe that the people that got replicated by the pod, first of all, didn't have any emotions. And that was something you had to spend some time around. And then they had something about their fingers were together. Okay, so the replication wasn't perfect. It's the same thing with the neural network. You're not going to get an exact replication, but you are going to get something which is pretty nice. Now, one of the interesting things, let's get back to this idea of training the oracle, and we haven't even addressed inversion. Everything I've shown you here is a forward problem. The neural network has been emulated on the forward problem of this acoustic model. Let me address a more general case. And that is the following. We are learning in an oracle the difference between, let's go back to our old idea of trees and shrubs, okay? So we get trees, and we get trees, and we get shrubs. And this is in feature space. Now there is something which divides the trees and the shrubs, which we'll call the concept. The concept is assumed to be truth. This is the actual boundary. You don't know what it is. If you knew what it was, you wouldn't have to train anything. We are trying to estimate this concept by the representation of the neural network. So we train a little bit and we get a representation here. And we would like to have sufficient data so that this representation eventually converges to the concept, right? Question is, how do we do that? Well, one of the things we could do, don't forget, our data is costing us money. This is an oracle. It's coming along, spitting out money. One of the things we could do, I guess I'm not a very good classifier. One of the things we could do is just keep on generating random numbers. In fact, this is probably where these things came from. You probably gave it some prior range of data that was useful to it, the height of the tree and the weight of the tree or something, and you generated these results. But you'll notice something very, very interesting is that if we want to get the representation closer to the concept, that is our estimate closer to truth, we don't really care about data that's way up here. If you give me a plant that's 100 feet high, I don't have to ask if it's a bush or a shrub. There's no ambiguity there, right? Where is the best results going to come in? The best results come in the closer you get to the boundary. So when you present me a bonsai tree, okay, you give me a bonsai tree, I might actually have it misrepresented here because the bonsai tree kind of looks like a shrub. So in general, what you have is the data which is close to the boundary is more information rich than data which is far away from the boundary. Data which is far away from the boundary are obvious cases. It's the data close to the boundaries that is the most confusion and the most information rich. So after we do this first result of the oracle, one way to do this is instead of penetrating the oracle with random numbers is to rather be more sensitive to the numbers that we ask it to generate. And one of the ways that we can do this is put in points which are close to this representation boundary, recognizing that we're going to get more bang for the buck if we put in points which are close to the boundary. So therefore what we can do is we can come over here to our neural network, and here's our neural network, and here's our X, and here's our output, which is Y. And let's suppose we're doing a classifier, and suppose our threshold for the output is equal to a half. In other words, anything above a half is going to be a tree, anything below a half is going to be a shrub, is what we're saying, or a bush. Well, what does this correspond to? Y is equal to half. This corresponds to a contour in the output, right? So if we can invert our neural network and we can get ourselves a bunch of vectors which give us a result close to a half, we are going to have a number of points which are close to the boundary. Therefore, a number of points which, once taken to the oracle, we will get information-rich results in order to modify our training data. So indeed, we do this. We train right here as our representation boundary corresponding to a threshold of equal to a half. We take these points, and these are the points and points close here now that we can take to the oracle, and we can get their identity taken care of, because the oracle will tell us what this point is. It's a bush or a shrub. In essence, what we're doing is we're training the neural network, and we're asking the neural network, what is it you're confused about? What is it that you don't know? And by this process of inversion, it's saying, well, here's what I'm confused about. I really don't understand this point. This point's kind of ambiguous. I got some problems with this point, etc. So we say to the neural network, no problem, we're going to take them to the oracle, the source of all truth, and we are going to generate the data now, and we're going to add this to your training data and clear up those ambiguities. And you can see that this can be a repetitive process, wherein one trains, one generates some additional training data, one trains a little more, generates additional training data, etc. Question?
When do you know that the first step is over, the step that generates the generalization? And why didn't you just not start off with some random path through the space and look at something local to that and see how far it goes?
I suppose you could. And I have to come up, I have to respond to you with an overused but albeit very true response, which is it's very problem dependent. Okay. First thing one does, by the way, when one obtains data is you sit around and you wallow in it for a while. You really do. You have to get out your MATLAB, you visualize it in cuts, and get around and play with it. You just can't take data and throw it at a neural network or a classifier or something. The more that you're able to play with it and get insight into the way that the data is packaged, the better. So my answer to you is that I don't know. In general, it's a good idea to do at least some partial training, so at least when you do the inversion, you know you're in the ballpark. And then you're defining what ballpark is, which is a heuristic also. Now, the question is, how does one generate all of these points given a partially trained neural network? That is, suppose the neural network is trained. Well, if the neural network is trained, what we do is as follows. We perform an inversion of the neural network by doing a search. You notice with training, what do? We fix the data. Okay? So that means we fix the input-output. and we wiggle the weights. In other words, the weights are our variables in training a neural network, right? At least the layer perceptron. So we fix the input, we fix the output, and we tune the weights in accordance to training and test data in order to give the best representation for mapping the input-output. What about inversion? Inversion is very similar. Notice we have the inputs here, we have the weights corresponding to the system, and we have the output. So for training, we fix this, and wiggle this. For inversion, what do you think we do? We fix this, because we're trying to invert a fixed trained neural network. We fix this, we fix that equal to a half, which is the output, and we wiggle this in order to find the input. So again, for inversion, we fix Y and W, and we wiggle the inputs, we wiggle X. Now there's some challenges associated with wiggling X. One of the challenges associated with wiggling X is that we have a number of problems, or we have a number of solutions. The solution isn't unique. So what happens, think for example, if we wiggled X, and how would we do this? We would actually look at the contour that we wanted. If we set Y is equal to some constant, we would look at the contour. One of the errors we could use was the value of the contour, say equal to a half, minus the actual output. That is f of x. This is the output. This is what we want. This is what we get. And if we square this, this would be a nice error function as a function of x, wouldn't it? Right? And if we minimize this as our error function, then we would obtain a result in which x, f of x, was equal to c. And it's nice and positive, so we can use steepest descent and such. But what does this look like? This will look like an actual trough. If we look at a value of c, for example, right here, this error function is a function of x, will look like a 0 here, and then if we go any direction from this 0, we'll be going uphill. So what happens if we use steepest descent? We will go to the valley. We will get to the valley. But the place we go in the valley is going to be a function of a lot of things. It's going to be a function of our initialization for our search. Clearly, if you started here, maybe you go here, right? And it would be a function of our step size and the search algorithm, etc. So we can indeed do the inversion one point at a time, and you could actually take the derivative of this and do steepest descent or another descent sort of algorithm. But there's another way you can do it, and think about this with me, and the solution becomes obvious. We're looking for a number of points. To do our oracle, we're not just looking at a single point. We want 50 points on there. And those 50 points are such that we want to take those 50 points eventually to the oracle. How can we get 50 points all at once? We can do 50 searches one at a time, or we can do one search 50 at a time, which corresponds to what sort of algorithm? Of course, corresponds to an evolutionary computation sort of algorithm. In other words, that's one of the interesting things, one of the great things about evolutionary computation. It has a number of agents. And if we're very clever in our inversion sort of process, we can actually converge to a number of points simultaneously using the evolutionary programming, so that a number of our chromosomes having different results will all be lying on this contour. Does that make sense? So indeed, that's a very good way of doing that. There is a problem, though, with that. And in fact, Eberhardt, when he did his inversion of his diseased neural network, actually used genetic algorithms. There's a problem with genetic algorithms, and let me show you the basic concept of the problem with genetic algorithms. Suppose we were trying to invert along a contour which looked like this. Yeah, I guess that'll do it. Okay, and suppose that we were attempting to invert along this contour here. Now you remember in the process of genetic algorithms, we had the idea of survival of the fittest, right? The survival of the fittest. Now, what is interesting is that you start out with a number of possible results, and the number of these possible results begin to churn in the genetic algorithm, and eventually, yeah, they're going to come closer here. But notice, interestingly, what happens. You have a very big area here, which you're going to have relatively healthy chromosomes, right? So if you stray really far from this boundary, you're still going to have healthy chromosomes. Whereas over here, where you're very steep, if you just take a little step away from the result, your chromosomes are going to die because they're not going to be fit because you go uphill so quickly, right? So what tends to happen in genetic algorithms where you simply use survival of the fittest, the strict sense of survival of the fittest, is that all of your solutions begin to congregate over here in areas where you have a very shallow gradient. And you don't get the solutions over here where you have a very, very tall gradient. Does that make sense? So that's one of the challenges of using survival of the fittest. So we must be a little bit more clever in doing this. And I'm going to show you an algorithm now that does exactly this. This is a presentation which is available to you on the home page. This is a presentation which is available to you on the home page. This is a presentation. There we go. Okay, this is one called Evolutionary Computing for Boundary Marking. And how come I can't go to the next one? Oh, I have to go over here. Okay. Okay, here's what we're going to do is look at the definition of the problem, the application, motivation, previous approaches. We'll look at the boundary marking algorithm, which is a technique which avoids its accumulation in the shallow gradients, and look at some implementation movies, very simple software. Some of this is actually what I presented to you. It's basically the equation of solving fx is equal to c, where c is equal to a given constant, and there are a number of solutions. By the way, this many times in inverse problems is referred to as being ill-posed, in the sense if you have a output that there's many inputs which can give you an output, that's ill-posed. Ill-posed is bad when you're looking for a single inverse solution. When you recognize there's a whole bunch of them and you embrace all of them, then it's no longer a problem that it be ill-posed. So that is indeed the problem that we have. Here are the contours, and again we're trying to go towards the contours. And then the way that it's done is to train a neural network, and we are going to actually apply the fx is equal to c to a neural network. Again, I emphasize this fx is equal to c is not restricted to neural networks. It's applicable to any memoryless nonlinearity that you have. That memoryless nonlinearity can be a neural network, but it can also be an arbitrary, very strange function that you're trying to invert. It could be a fuzzy system, for example, too, right? Wherein x was your input and c was a fixed consequent for the output. You would like to find in all of the values for fuzzy membership functions that would give you that output. So you can invert fuzzy inference engines also. We're going to specifically apply it to the neural network for the reason of the oracle. The oracle is referred to as a query-based learning because we are actually asking questions of the neural network. So we're making queries to it. And it does boil down to a solution to the can't teach an old dog new tricks. What do I mean by that? Well, suppose that you have one of these classification spaces trained, and you're just generating numbers by random. When are you going to learn something new? Only when you get a point which is close to the current representation, the current boundary, right? that is misclassified. Now, in the beginning, you're going to have a lot of that happening because you're not going to be zeroed in on what's the result. After you've trained for a long time, that representation is really close to the concept, and in order to get something new, you're going to have something which is between the representation of the concept, which makes it very, very difficult to teach that old dog new tricks. So that's the idea. You can't teach an old dog new tricks. So indeed, if that's the case, let's stay away from the random number generation and actually generate these numbers in an intelligent manner. We're asking a neural network, what is it you don't understand? Invert the neural network around f of x is equal to a half, assuming that this is the threshold that we've chosen for our ROC curve. And here is in 2 dimensions the concept of a representation, which is what the neural network is trying to learn, and the concept, which is the actual truth, in this case is elliptical. And we only have certain instances of this. The idea is through the neural network on this representation to find points on the boundary and then take these points to the oracle in order to clear up the ambiguities which might exist. So you take it to the oracle, which in this case looks like a clown, who will tell you that it means this, and you use the new result to fine-tune the neural network, and this process can be done an iterative number of times. This is what the Eberhardt paper was doing as far as the inversion in medical diagnosis, and also Huang, Professor Huang in our department. We worked together, Professor Atlas, Professor Huang, Professor El-Shikari, and I worked on some of the early work on neural network inversion. And Jianning Huang went with Yuri Wagner's and did some very nice control work using inversion of neural networks as the plant model in control systems. So that's another place that inversion is useful. A place where the CIA lab has used it in, CIA is Computational Intelligence Applications. It's Professor El-Shikari's in my lab. Is in the area of security assessment, wherein one looks at the operating point of a power system, and there's a safe area, there's a warning area, and if you get in blackouts and brownouts, you have problems. So we were actually trying to train a neural network to do something like we saw with the insonification, because determination of these characteristics involves solution of a number of simultaneous nonlinear equations with ugly boundary constraints. So that's another place that it can be used. Okay. Techniques of inversion, we mentioned doing it one at a time. There's a problem with that. We also talked about using genetic algorithms, and the problem with that is the unwanted clumping. The unwanted clumping occurs wherein you have these shallow basins. All of the life forms tend to accumulate there because even though they're far away from the boundary, they're relatively fit. Here's an algorithm which is actually generated by Russ Reed, the author of the book that you have along with me. And this is his algorithm. Here is the error, and the concept was as follows. We would take points that survived and we would add noise to them. You remember with the genetic algorithm, what we did was the crossover and the mutation. That's the way we found new things. A very common way of generating new points in evolutionary computation is to take a point and then splat a bunch of offspring around it. And that makes a lot more sense, at least in a geometrical sense. My mind is stuck in an L2 rut, so that makes sense to me. So that's the concept, is to splat out these new results using noise. But even this is not going to take into account these shallow basins and survival within the shallow basins. So the idea was as follows. There's 2 things that we want to do. Number 1 is we want points on the contour. Number 2, we want them separated from each other. We want them to keep from clumping. So when we talked, we actually talked about giving the points bad breath so they wouldn't actually accumulate or get close to each other. So we had to repel them in some sort of fashion. So those were the things that we would like to do. We'd like to repel the crowded points. And the way that one repelled the crowded points was to calculate for all of the n vectors the distance between nearest neighbors. And what you wanted to do is you wanted to make that parameter large, or at least equal around. And then we also wanted to avoid the shallow basin. So the new numbers were taken and they were generated actually upon a gradient which was tangent to the original line. Let me give you an example. In fact, I think the next slide is an example of that. Okay, here's the concept. Here's a clump. So we had a parent, and it spit out randomly a number of points, and we can determine the result of each of the points. What we're going to do is look at each of these points, and we're going to decide whether we need to get away from the crowd or whether we're okay where we're at. If things are too dense here, we need to get away from the crowd. The way that we get away from the crowd is actually compute the tangent vector to this gradient and move that point along the tangent. Moving it along the tangent will roughly still keep it on the contour. Not exactly, but it's our best approximation to still keep it on the contour. And we only did this if indeed the points were sufficiently crowded in order to do that. And so this became the new result. What do you mean ding ding? And this is the actual math of doing this. First of all was a vector which was tangent to the original function. Remember, we could get the normal vector. What's the normal vector? That's the steepest descent vector, right? If you look at a tangent, if you look at a contour line, you're standing on a contour line doing steepest descent. When you take a step downhill, that's orthogonal to that line. You're going 90 degrees, you're going downhill. So that's the normal vector. That's something we can compute relatively easily. And then once we have that, we simply subtract off the projection of the vector onto the normal vector, make a unit vector from that, and then we take a step size tangent to the line in order to stay along the contour. And this is how we got the x sub k by x plus double x. And so the process is as follows. You generate n random points. You kill m of the points with the worst errors. This is survival of the fittest because you don't want it too far from the contour lines. You generate m new points by selecting parents from the least crowded points. From an average distance to the m nearest neighbors is how we determine the nearest points. And again, doing this and doing it this way avoids undesired clusters in the shallow regions. Generate the new points by just adding noise and repeat the process. Okay, I don't care. Oh, I know what I need to do. There we go. Okay. Next thing is to repel the crowded points, and this is exactly what we talked about, is computing the normal vector, finding out the gradient normal to that. Remember, the gradient was the partial with respect to the parameter, and then we found the normal with respect to that, and then used that to actually compute the step size, which was tangent to the original result. Okay. Now let me show you some actual interesting results here, if I can. These are just some simple simulations in 2 dimensions. And you got to watch quickly. I hope that this works very well. Just want to run it where it's at. It's a little DOS program. Do you want to install? Yeah. Okay, you got to watch it. Now, in this software, you can actually look at the parameters in the manner that they're generated, but I don't know if you can see them on the screen. I think you can see the lighted values. Okay, you're going to see my bald spot, but don't worry about it. Oh, you do? Okay. Okay. If you actually look at this, you should be able to see little points on here, which are actually, in fact, you can see them off screen. They pop up around here every once in a while. And you can see them being generated randomly, but when they pop up, They just pop up and disappear because they die. They're too far away from things. Another interesting aspect about this is these points are relatively close to the boundary, but you'll notice some things which are in here, and this is actually not a boundary. This is the boundary. These are actually Gaussians, which are cut by a plane. And what we have here is a very shallow valley here, so that if a point gets in here, well, it's not exactly on the contour. It's not exactly 0.5, but it's like 0.48 or something. So there is survival which exists here. Now what I want to do, please just keep that where it says. I want to show it to you again and have you watch the convergence, because it was initially randomized randomly. How else do you randomize? I guess randomly. Okay. Run this program. Okay. Now if you watch it, all the points start very far away. What? It's performed an illegal operation. I don't want details. I don't care about details. Okay, here's what I'm going to have to do. I have to actually save this. I'm going to save this. And I'll save this. The audience is growing restless. Okay, now what I will do in this real-time programming world of ours is I will go to 523 and I'll generate it directly from here. Let's see, here's the island two-dimensional. Another illegal operation, huh? Okay, you don't want to see it again anyway, do you? Here's another one. Let's see if this does an illegal operation. It did an illegal operation. Okay, come here. How do you do that? Where's the DOS prompt? There it is. DOS prompt, okay. Okay, now what do I do? Okay. Well, you know what? My thunder has been stolen. I think maybe I just need to reboot. And I'm going to tell you what happens. Restart. And let me show you, as we restart, roughly what happens in these scenarios. It's exactly as you might suspect it would be, is that there are these contours, and one initially starts with just random number generated points, randomly generated points, which one attempts to find for the solution, and then all of the weak ones are killed off. So this one's dead, and maybe one out here dies, and then the rest of them actually generate offspring. Then the and then we didn't go over the projection, but there's a projection onto this contour by these points. And herein we have the clustering. If it's too finely grained, a tangent is generated, and the new point is instituted here. And the step size that we have here is a lot like gradient descent. Let's see, in the task. Okay. Dumb computer. Okay, there we go. So anyway, we see in these two-dimensional cases where we can get these results very nicely. But if you think about a two-dimensional case, that's not that big of a deal. I mean, you could take a two-dimensional function, do a little mesh plot in MATLAB, and probably just point to the inverse points, right? So what do you do with, why is this important? The importance is inversion in very high-dimensional spaces. And I had another example, which maybe I'll get to show you, which is in the 59-dimensional space, wherein we have a contour in a 59-dimensional space actually trained using power system emulations. We're attempting to find boundary points. in this 59-dimensional space in order to assess security of power systems. And it boils down to be exactly an inversion problem. Now, how would you monitor the performance of an inversion problem in 59 dimensions? Well, we chose to do it two ways. Number one was to look at the average distance from a point to the contour. Doesn't that make sense? That would be one thing you would do. And the second thing you would do is monitor the average distance between points. If the average distance between points got to a constant and began to, what? What? What's it doing? Not scanned, possibly infected. Man. So anyway, there were histograms of, what is that? So one was to look at those, but then to look at the histogram. Now, if we come to a result that we like, what would you expect the histograms for the average distance to the surface to look like? You would hope that histogram would be a delta function slammed up against zero, right? Right? Because you want everything on the boundary. In order to have them equal distance to each other, and you looked at the histogram to the nearest neighbor, each point to the nearest neighbor, you would hope that that would be a constant shifted to a point where they would be all equal distance from each other. So in other words, what I'm saying is that what we would hope is that if we looked at the histogram for the distance of all of the points to the contour, it would be a value which is right at the origin. If we were to look at the nearest neighbor distance, we would hope it would be a constant, that all of the points would be equally spaced on this hyperdimensional surface. That's something that we would like to see. Now we'll see if that works. I'm going to try this one more time. If it doesn't work, then that's life. Let's try the island again. Let's see if that works. Ah, here we go. Whoa. Okay, so you see it work. I'm going to do it again. Watch it. You can see it's randomized initially, and then all the points begin to gravitate towards the contour, which is exactly what you would expect to do. And they sit there and percolate as an artificial life form. Yeah, artificial life, right. Here's another example. This one actually is a little bit simpler. It's a two-dimensional edge, but it has a similar sort of thing. And you can see all of the points generating on the result. We used this actually to show one of the, we actually had a lot of problem with this. We wanted to make sure that the points were on the contour but inside certain intervals. And how would you do that? Well, guess what? The final really, it was one of those solutions you got to and you said, oh yeah, of course. If something went outside the box, which you can see it doing here, you see them popping outside the box here? You just kill it. You just don't allow it to live. So you get a little guy out there with a hammer that whacks everything that goes out there. Okay, let me show you the 59-dimensional space example, and we'll have to zoom out for this a little bit. Yeah, we'll need the whole screen here. I'll actually initialize it again once we get done. But this is the histogram for the closeness of the points to the contour in the 59-dimensional space. And as we would expect, it's all zero. This is a histogram of the points in terms of nearest neighbors. Again, would like this to be a delta function, or at least very, very narrow, and you can see indeed we're doing this. Now, the top point is actually the means, the center of mass of these two histograms. So you can see one of the histograms should go to zero and the other one should go to a constant. So the red one is going to zero, so the red one corresponds to the distance to the boundary, and the other one is the mean of the distance to the nearest neighbor. So indeed, the algorithm is working very nicely in this 59-dimensional space in order to perform the inversion. So this is an example of using a neural network to perform inversion, using evolutionary techniques to perform an inversion on a static, memoryless sort of neural network. Are there any questions at all? Okay, hearing none, we'll dismiss the class. Thank you for your attention.